In this video, I'll cover the basics of affect recognition. I'll discuss some common feature types and how they might be used in a supervised affect recognition system. So far in this module, we've focused on sentiment, which is one specific dimension of affect that seeks to determine whether a specified text sample evokes positive or negative emotions. However, there are many other types of affect that we can generalize our sentiment-based tools to. Common and useful types of affect recognition also include things like emotion detection, personality detection, and stance detection. At its core, affect recognition simply seeks to determine how a given text sample or interaction makes one feel based on some specified range of affective categories. As we've already seen, affect recognition and its varied subtasks are most commonly framed as supervised text classification tasks. Given a labeled dataset, a classifier learns which input patterns correspond with different classes and uses those patterns to make predictions for new unlabeled inputs. With large datasets, features like unigrams or bigrams paired with a logistic regression classifier can work quite effectively for this task. With very large data sets, for example those with many millions of words, using all unigrams or bigrams could be computationally impractical, so researchers will often prune the set of n-grams included as features. A common way to do this is to retain only n-grams that exceed a corpus frequency threshold or that have high point-wise mutual information with a specific class in the training data. The equation for computing point-wise mutual information is shown here. Essentially, you divide the probability that an n-gram X occurs in class Y by the product of the probability that the n-gram X occurs across the entire corpus and the probability that the class Y occurs across the entire corpus. Then you take the log of that. On the other hand, if we're working with a small data set, n-gram features may not be the best choice because they tend to result in sparse feature vectors. In these cases, it may be a better idea to derive features from external lexicons. Some ways that we might incorporate lexicon-based features in an affect recognition model include using a simple binary indicator function, where a given feature associated with a lexicon L will be assigned a value of 1 if the input X contains a word from the lexicon L, or a count-based function where a given feature will be assigned a value corresponding to the total number of times that a word from the input X exists in the specified lexicon. In some external lexicons, words are associated with scores or weights. In those cases, we can incorporate those weights into the count-based function by adding a simple multiplication factor, theta with a subscript of W and a superscript of L, corresponding to the weight or score of a word W in the lexicon L. An advantage of using lexicon-based features is that they can lead to interesting psycholinguistic insights, especially since we have lexica available for a diverse range of different characteristics, such as sentiment, emotion, personality, word difficulty, word concreteness, and so forth. For example, we might find that count-based features associated with sentiment scores are closely correlated with count-based features associated with extroversion scores, and from this we might extrapolate that more positive language is also more associated with extroversion. The opportunities available with this type of analysis are wide-ranging and compelling, and useful for shedding light on many interesting social science problems.